Welcome to the Satellite Fundamentals course for GOES-R module, Visualizing the Geostationary Lightning Mapper in AWIPS. The 30-minute Introduction to the Geostationary Lightning Mapper module is a prerequisite. Dr. Jeffrey Stano assembled this 10-minute module at NASA's Short-Term Prediction, Research and Transition, or SPORT Center. There are 3 goals for this module. First, briefly describe the difference between the satellite-based Geostationary Lightning Mapper, or GLM, versus ground-based lightning detection networks. Second, list the initial products that will be available. The module concludes with a brief glimpse at the initial display of the GLM observations in AWIPS. 3 ground-based networks are currently available in AWIPS, including the National Lightning Detection Network, or NLDN, Earth Networks, or ENTLN, and the Regionally Limited Lightning Mapping Array, or LMA. Observations from these networks will differ from the upcoming Space-Based Geostationary Lightning Mapper, or GLM. It is important to be aware of the unique strengths and limitations of these networks. The National Lightning Detection Network is likely the most well-known, covering the continental United States and the nearshore waters with greater than 95% detection efficiency of cloud-to-ground flashes within 200 kilometers of CONUS. The NLDN updates every minute and has an average location accuracy of approximately 200 meters. Within AWIPS, the NLDN shows the point locations of cloud-to-ground flashes, which can also be selected as a density product, and whether or not the cloud-to-ground flash was positively or negatively charged. The NLDN may receive some AWIPS updates in the near future. These updates could include plotting each return stroke of a flash. Also, the NLDN observes some fraction of intracloud flashes, but these data are not presently available in AWIPS. The Earth Network's Total Lightning Network became available in AWIPS during 2014. The ENTLN detects some fraction of cloud-to-ground lightning globally because it includes observations from the Worldwide Lightning Location Network. The best ENTLN coverage is over the continental United States and nearshore waters, where the network detects greater than 90% of cloud-to-ground flashes and greater than 50% of intracloud flashes. The ENTLN has a 1-minute temporal update and approximately 500-meter location accuracy. Within AWIPS, the ENTLN displays both cloud-to-ground and intracloud flashes. Uneven sensor distribution results in some detection efficiency variability across the network. AWIPS currently provides 3 basic display features. First is the point location of the cloud-to-ground and intracloud flashes, which can be selected as a density. Second is the polarity of the cloud-to-ground flashes. Lastly, the raw pulses or lightning flash components can be plotted to add spatial extent. The lightning mapping arrays have been available to some National Weather Service offices. LMA networks typically have a range of 250 kilometers from their center. The LMA networks provide detailed 3-dimensional mapping of intracloud lightning channels and the intracloud components of cloud-to-ground flashes. LMAs observe tens to thousands of geolocated emission sources per lightning flash. The detection efficiency is in the upper 90% for all lightning at the network's core and then degrades with range. Operationally, the lightning mapping arrays update every 1 to 2 minutes, with a location accuracy of tens of meters that degrades with range from the center of the network. Within AWIPS, the raw sources or components of a flash are shown as a density product revealing the full spatial extent. The sources can be combined into flashes, which better relate to the updraft intensity and viewed as a flash extent density. A pseudo-geostationary lightning mapper demonstration product has also been created, but will become obsolete once the geostationary lightning mapper is operational. The Geostationary Lightning Mapper will be the newest lightning observation system and is set to launch on the GOES-R series satellites. Geostationary Lightning Mapper covers most of the GOES field of view from 55 degrees south to 55 degrees north. The GLM will observe both cloud-to-ground and intracloud lightning. The spatially uniform detection efficiency exceeds 70% during the day and 90% at night for all lightning. GLM lightning observations will be available in AWIPS within 20 seconds after the lightning occurs. The GLM observations will be reported on a grid with a spatial resolution ranging from 8 kilometers at nadir to 14 kilometers at the edge. Within AWIPS, the GLM will not differentiate between cloud-to-ground and intracloud flashes. Rather, AWIPS will display the locations of lightning events, pixels illuminated during a 2-microsecond interval, groups analogous to return strokes, and flashes. Additional GLM visualizations beyond these initial capabilities are under development. The AWIPS OBS menu contains all available lightning observations under the lightning heading. Options then appear for each of the various lightning observation systems. The plot of cloud-to-ground flash locations from the National Lightning Detection Network has been in AWIPS since the 1990s. A gridded option also is available. The Earth networks, or ENTLN data, show the cloud-to-ground blue and intracloud orange flash locations. Lightning mapping array observations also are available to some NWS offices. The various networks can be found under the Standard Products option. The lightning mapping array source density contours all of the radiometric emission sources, or pieces of a lightning flash, that the LMA locates. The GLM data are available under the GLM Lightning menu, and users can select from the various products that will be detailed in the following slides. The Geostationary Lightning Mapper is the first instrument of its kind available in geostationary orbit, so no real-world example exists. This module uses the best available demonstration product. This Geostationary Lightning Mapper proxy dataset, developed by NASA's Marshall Space Flight Center as part of the Algorithm Working Group, uses a combination of the lightning mapping arrays and the low Earth orbiting tropical rainfall measuring mission lightning imaging sensor. As such, this module provides a first look of our best demonstration of the GLM appearance. AWIPS will initially display GLM events, groups, and flashes using the GLM plugin. To start, this plugin will bin each observation into gridded density products. The GLM visualizations will evolve once real-time GLM data are available. The following slides describe the initial visualization capabilities and more advanced features under development. The most basic geostationary lightning mapper observation is the event. An event is any illuminated pixel during a 2 microsecond period. Although events correspond to pieces of a lightning flash, they do not have a direct corollary in the ground-based networks. The closest approximation would be the lightning mapping array sources, or Earth networks pulses. This example shows the 1-minute GLM event density at the native 8-kilometer resolution and reveals 3 main features. The greatest event density is coincident with the strongest storm updraft. The developing convection can be easily identified, and the spatial extent of lightning is evident. A geostationary lightning mapper group is an intermediate observation that represents a cluster of events based on temporal and spatial criteria. The group location is a radiance-weighted mean of the events that comprise the group, which places the group closer to the brightest portion of the flash. GLM groups are most similar to the National Lightning Detection Network strokes and Earth Network's cloud-to-ground strokes and intracloud pulses. This AWIPS example of the 1-minute density of all groups reveals similar features to those shown by the events, with a slight shift in location due to the optical intensity-weighted group locations. Geostationary lightning mapper flashes are clusters of groups in time and space and directly correspond to the flashes reported by the ground-based networks. Like the groups, GLM flashes are a radiance-weighted mean of the groups that comprise the flash. This example shows a 1-minute summation of all flashes as a density product, revealing several features. A GLM flash plots the flash centroid and is shown in one grid cell only. As a result, flash density grids do not indicate the spatial extent of lightning, like the event and group grids. The biggest advantage to the GLM flash grids are that the lightning flash rates are more closely related to the updraft and storm intensity than the GLM events and groups. This GLM proxy case comes from March 2, 2012 in the Huntsville, Alabama County Warning Area. The initial image at 1430 UTC shows the 1-minute density of GLM flashes in the upper left, groups in the upper right, and events in the lower left, along with the radar reflectivity in the lower right. The GLM proxy observes the initial electrification as evidenced by the sporadic, small density values. This example GLM flash has 5 events clustered into 2 groups. More total lightning is observed 4 minutes later, indicating intensifying storms. The GLM event and group grids are identifying the strongest storm updraft, as well as the spatial extent of the lightning activity. 13 minutes later, at 1447 UTC, a continued increase in the density of GLM events, groups, and flashes within one storm updraft indicates rapid intensification of this storm, signifying the potential for severe weather from this cell. Animations help further explore this example. The display is identical to the previous slide, only the animation now covers a 60-minute time period from 1430 to 1530 UTC on March 2, 2012. This example shows the storms as they develop and expand while traversing the domain, revealing that the GLM proxy highlights the most intense storm while providing insights on the weaker convection. AWIPS includes the ability to toggle a gridded display from a raw, gridded product to an interpolated image. Forecasters can quickly toggle between these visualizations, which is accessed through the imaging option. Previous assessments indicated that forecasters appreciated the interpolated images for visualizing the strongest storm cores, as evident in this example. This module provided a basic overview of the Geostationary Lightning Mapper's display in AWIPS. The AWIPS products and displays will evolve once the GLM is launched, based on product developer and forecaster feedback. Once GLM is launched, operational example modules will be generated. Some future applications training modules will include a flash extent density to show trends in spatial extent, automated lightning jump algorithm for severe weather, as well as lightning safety for both outdoor events and aviation applications. Job sheets and integrated training in AWIPS also will be included after GLM's launch. Additional information on both GOES-R and the Geostationary Lightning Mapper are available on the web at the links below. Thank you for your participation in the Satellite Fundamentals course for GOES-R module, Visualizing the Geostationary Lightning Mapper in AWIPS.